rule called? Because I went, is that PEMDAS?
It is.
I went nuts trying to figure
No.
I did all the work.
It's PEMDAS. It's just, it's not a rule. It's just the way that the calculator is set up, right? The calculator is not set up, and somebody showed me that there are some calculators, scientific calculators that have. Can somebody shut the door? Thanks. There's scientific calculators that actually have the big bar. It's kind of nice. So you can see what's on the top. But ours, this one doesn't, because it's got all this other stuff. There's no room for that kind of thing to hardwire. So you just have to tell it what the top is divided by what the bottom is. You have to tell it. It's unfair for it. We have an advantage. We have eyes, so we can see the big bar. It can't see it, so I got to tell it this is the top, this is the bottom. Right?
Well, when we're actually doing, when you see the problem, you're actually doing it by hand, as opposed to you doing it on a calculator. I was trying to figure out what rule it was because I actually did it.
It's not a rule. It's just yeah.
I did it right, and I came out with two different answers, and I was.
It's not a rule. It's just what that big bar represents. Writing it like that is not the way you write it in the calculator. So it's not a rule. It's more of a semantic thing. It's more of a syntax thing. Yeah. Cool. Any other questions or comments or? All right, let's do a couple of these, because these include some of your favorites, like the distance, rate, time problems. I know.
You said section 3.3?
3.3. So just kind of a summary real quick. What we've done, 3.1 is substitution and graphing, I think if I remember correctly. 3.2 is elimination, and then 3.3 is applications, word problems, right? So look at number 38, for example. It says that Alvin paddles 4 hours with the 6 kilometer per hour current to reach a campsite. The return trip against the same current took 10 hours. Find the speed of Alvin's canoe in still water. That phrase always freaks people out, but the speed of the canoe in still water. Yeah, that just means that he's not really going, he's going with the 6 kilometer an hour current, so his speed is faster than what it would be without the current, obviously. Right? If anybody's ever kayaked, you can actually turn that bad boy around and get to a point where you're paddling, but you're not going anywhere. It's actually kind of cool in white water to do that. Here's a nice way to kind of organize. The problem with these kind of problems is there's a lot of information going on. So I don't know if you guys, if you've done this before, you don't like it. If you've done it before, you like it. You can do it a different way. I kind of do like the little chart dude, personally. What's the equation that relates distance, rate, and time?
Distance is rate times time.
I like it. Dirt, right? D equals RT. Dirt, right? So rate times time equals distance. The nice thing with the chart is you just fill in what you know and then see what you don't know. You can step back and see the white space and go, I don't know that. Shit. Why do I have 2 rows here? Because there's definitely 2 situations. There's one with it, going downstream, and there's one going upstream, right? So there's a downstream and there's an upstream. Where can what's the thing, what's the problem here? What's the unknown? What's my variable going to represent?
That's speed.
Good, it's the thing I don't know, the speed of this canoe in still water, right? So what do you want to call that?
X.
X, I love it. So how fast is he going? What's his rate of movement? How fast is he going with the current, going downstream then? Beautiful. The speed he's going without it plus it. Cool. So real quick, on the upstream, when he's going against the current, how fast will he be going? How fast he normally goes, minus that 6. Because he's going against it, isn't he? And again, if he paddled exactly 6 kilometers an hour, how fast is he moving? 0. He's staying in place. It's sort of like turning around on one of those things in the airport. You're just kind of walking. Pushing people out of the way. Now, what else do I know?
Time.
Yeah, the time we know for sure. That's awesome. Whenever we know something definite, paddles for 4 hours here, right? And it makes sense. It takes him longer when he's going against the current. That makes sense. It's going slower, so it should take him longer. You can always double check and make sure this makes physical sense. Now, here's the funky thing. You do what the formula says to do. And the equation comes from how these things relate. Now, of course, he went to a campsite, and then he went back. So how are the two distances going to relate? So the equation is going to be this business equals this business, right? So what is this business here?
4 times x.
I like it. Distance is rate times time, so 4 times this. And here this would be, now what did I just, well, I'll do that. I don't care. So I'll show you a different way to do the same problem using more than one variable. Me, I kind of always go to the single variable thing. I like that better. But so what we just said, we said that this must equal that. Oops. And then you can solve that from there, right? Now, to do this with 2 variables would kind of be silly. And I'll show you why it would kind of be silly in a minute here. Well, what do we get? We can solve this bad boy. Yeah, so if you subtract 4, you get 6x equals, add 60. So x equals 14.